All right, good morning, everybody. So let's go ahead and do a quick review of what we learned last time. Last time we did a little exercise in class where I told you all to take a carbon atom and put 4 of the different colored spheres on it. And so we all ended up with something that looked kind of like this, right? And then I went around the class, well, not the whole class, but 4 of you, right? And what did we find? What was the discovery when I went around and compared my molecule to your molecules? Pardon? Yeah, so ours were the same if I recall right, and ours were different, right? And then I went to 2 other people and matched with one, didn't match with the other, right? These kind of look the same, but they're not, are they? One of them is like my left hand, and one of them is like my right hand, right? And so if I think about it, they are mirror images of one another, aren't they? My left hand is a mirror image of my right hand. You all know that. You can go into the bathroom and hold your left hand up. How many of you actually went and did that? Anybody go and actually do that? Yes. And what was reflecting back at you was your right hand, right? And so these are mirror images. Well, everything has a mirror image. But what's special about these? What's special about these is that they are non-superimposable. I can get the carbon atom, the white sphere, the green sphere to line up, but I can't get the blue and the reds to line up. They have handedness. Just like my right hand will not fit into a left-handed glove. These are different. Okay? And so what did we call this concept? Well, they are enantiomers, but what's the concept of not being superimposable with yourself or with a mirror image of yourself? Chirality. Yeah, so this is a chiral molecule. And we learned that if we had 4 different things around a single carbon atom, that it would be chiral, right? And so we're going to expand on that today. And right now we're talking about what I've got in my right hand and what I've got in my left hand, but we need to figure out how do we name these, right? Because right now all we could name this is blue, green, red, white, methane, right? And the same thing for here. But we know that they're not the same, so we have to have a way of naming these things. And so we're going to learn about what's called the R&S nomenclature today, okay? So we're going to talk about nomenclature for enantiomers quite a bit. So here's some other examples of things that you might learn about when you get into biochemistry. This is leucine. It's an amino acid. All of the amino acids are chiral with the exception of glycine. So when you all get into biochem, you're going to learn about these 20 naturally occurring amino acids that we typically consider naturally occurring. Leucine is one of them. This is just an example. It's an amino acid. Why do we call it an amino acid? It's got a carboxylic acid functional group. It's got an amino functional group. And then, it's all connected to these things. But it's a chiral molecule. If you look at the carbon atom right here, it has a nitrogen attached to it, a hydrogen, a carbon, and a carboxylic acid group. Those are 4 different things around that. And so it and its mirror image are in fact non-superimposable. And that star is either, you'll hear me use the word chiral center or stereogenetic center. They mean the same thing. Okay? And so that's where the chirality is. Okay? 3-bromohexane is another example. Why is that molecule chiral? Why is that carbon chiral?
Because of the spatial arrangement of the hydrogen and bromine.
Okay, that's true. I've got a bromine, I've got a hydrogen, but I got a CH2 here and I've got a CH2 here. What's different about it? What comes after the CH2, right? This is a CH2CH3, this is a CH2CH2CH3. They are, in fact, different groups that are attached to that stereogenic center. Okay? And so it and its mirror image are, in fact, non-superimposable. What does the solid wedge mean? Coming out of the plane of the paper, out of the plane of the screen, whatever, right? The dashed wedge, it's going away, right? So it's going away from me. It's going behind the plane of the board. And everything else that's drawn like this is in the plane. That's right. So you're going to learn a lot of this stuff about 3 dimensions that you probably didn't think you were going to learn in organic chemistry. So again, structure is very important. I want you to take just a minute or two with your neighbor, and I want you to identify the chiral centers in each of the following molecules if they have any. What about the red molecule? Does it have any chiral centers?
Got one.
It's got one. Where is it?
C1.
C1. Or is that going to be C1 or is that going to be C1? Just tell me what's attached to it.
Bromine.
The bromine. Okay. Why is that a chiral center? You're right. But why is it?
Got four different groups attached to the carbon.
Okay, what are they?
Bromine, hydrogen.
There's a hydrogen that's not drawn, which is important. You all have to remember that, right? And what else?
And then two different carbohydrate.
Yeah, so we have a carbon here that has no hydrogen, it's carbon alkene. And then we have a CH2 here. So those are four different things attached around that, right? And so we can have the left-handed version and we can have the right-handed version, right? We can have two things. I didn't draw it that way, right? But you could have the left-handed version or the right-handed version. That is the chiral center. How about the yellow molecule? It is not chiral. There is no carbon atom on that particular molecule that has four different constituents attached to it. And in fact, if you made this molecule with your model kit, what you would find is that it has a mirror plane of symmetry down it. Remember last time we said we can't have mirror planes of symmetry. We can't have planes of symmetry within a molecule that is chiral, right? And the example I used was myself, right? We all agree that my right hand is an enantiomer, my left hand. They're non-superimposable mirror images. But I'm not chiral because I have a mirror plane, again, ignoring my blemishes, down through my body, right? So I have a mirror plane. So me and my mirror images are perfectly superimposable on one another. If I could 3D print my mirror image, I would be able to turn it over and line everything up. It would be just fine, okay? How about the blue molecule? How many chiral centers does it have? How many? 3? I'll say at least 3. Here it is. Where are they? Tell you what, I'll go around the ring and you all tell me when we hit a chiral center. Is that a chiral center? It is not. Why?
It's double bonds of oxygen.
Yeah, so it's like it's attached to two oxygens, and those are the same thing, right? So it can't be. So no, that's not. How about this? Yep, there's one. How about this? There's one. How about that? Uh-huh. How about that? Why not?
It's only about two.
Well, it's got four things attached to it, but it's got two of the same thing, right? It's got two hydrogens attached to it, so that can't be. And how about this one? Yep, that's a chiral center as well. All right, so that has four different things attached to it. If I told you all to build this molecule at random at each chiral center, how many molecules do you think we would have made if I went around and compared everything? A lot. That's true. A little more specific.
8,
You think it's 8? Why do you think it's 8?
because there's at least 2 arrangements for each chiral center.
Ah, okay, you're right. So there are 2 arrangements for each chiral center. I can either have the left hand or the right hand. And I've got 4 chiral centers. So you might think 2 times 4 is 8. Close, but no cigar. Right? It's not 2 times 8. It's 2 to the 4th. It's not 4 times 2, it's 2 to the 4th. I've got 2, she's absolutely right. I've got 2 choices for the first chiral center, it can either be left-handed or right-handed. I have 2 choices for the second chiral center, it can be left-handed or right-handed, and so on and so forth. But that's not 2 times 4. That's 2 to the power of 4, which is equal to what? 64? 16. Yeah, right? We would have made 16 different molecules. A maximum number of 16 different molecules. There are cases where things would be, but this one would be 16. Remember when I showed you sugar last time? How many chiral centers it had? A lot of them. I forget how many there are. If Mother Nature made every one of those bonds statistically just 50-50, you'd have all these different types of sugar and only one of them would be sweet, right? And that's not how Mother Nature does it. Mother Nature knows how to put those atoms together in 3 dimensions correctly. And that's cool. And so even though there's over 100 possible different types of sugar, Mother Nature makes only one. Okay, she's really very good at it. Okay? The formula that you need to know here is that the maximum number of stereoisomers is equal to 2 to the n, where n is the number of chiral centers. I can almost guarantee you that question will be on an exam, where I will give you a molecule, you will have to identify the number of stereocenters, and you'll have to tell me what the maximum number of stereoisomers is. Okay? It's about as complicated as math gets for us. But you remember Taxol had a lot of chiral centers that I showed you last time. And chemists had to make one of those molecules, and only one of those molecules. And that's why it took decades to figure out how to take crude oil and convert it into Taxol. And Taxol, of course, as we learned, was a very potent anti-cancer agent. So it was important to be able to actually make something like that, right? Any questions about this? I'm getting the sense that you're pretty good at identifying chiral centers. So I'm happy with that. Now let's move into seeing if we can figure out how to name these things. Because right now we've been talking about the left-handed version and the right-handed version, right? But you should have asked me, what makes this left? Right? Why is that left and this one's right? Well, it's random. Than how I'm doing it now. But we have a way of actually doing this, and we call this the R or S stereochemistry designation. Okay? So, when you have a chiral molecule and it is drawn as a single enantiomer, you can determine whether or not it is R or S using some rules. And these rules are called the CIP rules. That stands for Kohn-Ingold Prelog system. You've already used this. I just didn't call it the CIP rules. When we were determining whether or not a alkene was E or Z and we figured priorities, that was using the Con-Ingold-Prelog rules. I just didn't say they're Con-Ingold-Prelog rules, okay? And so we're going to use the Con-Ingold-Prelog rules, and what you have to do is you have to determine priority based on atomic number, just like we did for the cis-trans EZ alkenes. So if I look at this particular molecule, right, and if I assume that each one of these colors is a different, let's say white is hydrogen and the other colored ones are the different halogens, right, I can assign priorities to these. I know that bromine has a higher atomic number than chlorine. Chlorine has a higher atomic number than fluorine, and hydrogen has the lowest atomic number. If you have a hydrogen on your chiral center, it will always be number 4. Okay? And we're playing golf here, not baseball. So higher the number, the lower the priority. Number 1 is the highest priority, number 2 is the second highest priority, 3 is the third highest priority, and 4th is the lowest priority. Okay? So keep that in mind. We're playing golf here. We want lower scores, right? That is the Con-Ingold-Prelog system. The first thing you're going to have to do is identify the priorities of the groups attached to the carbon atom. Okay? Now, until about the 1950s, all of these configurations were what we call relative. Okay? Left-handed versus right-handed. We didn't really know how they were pointing in 3 dimensions. We just knew relatively how they were pointing in 3 dimensions. I knew that the red and the blue were not really pointing in the same direction. Okay? And in fact, this will haunt you a little bit in biochem, because for whatever reason, the biochemists hold on to the 1950s. Okay? They will use a nomenclature that's a little different than R and S. When you start learning about the amino acids, they will not say an R amino acid or an S amino acid. They will say D and L. The D amino acid, the L amino acid. And we know that all the L amino acids are the natural amino acids, and that only bacteria use the D amino acids. You'll learn all that stuff, okay? Just know that D and L is the same thing as R and S, except you can't really figure out how things are pointing in 3 dimensions. That's the relative arguments, relative to a standard compound, okay? But now we know how to use our magic microscope to determine the absolute configuration. I can go get a crystal structure, I can put it on an X-ray diffractometer, and if I'm lucky, I can get a good diffraction pattern, and I can determine the absolute arrangement of those atoms in space, and it's kind of cool, okay? All right, so let's look and see about assigning some priorities to things. You will run into examples where the chiral center, or the stereogenic center, right? Clearly we have 4 different things attached to it. It's almost always going to be easy to figure out the lowest and the highest. Oxygen is number 1, hydrogen is number 4. Now I got to decide between the 2 carbons which one's 2 and which one's 3, right? Well, this carbon is attached to another carbon and 2 hydrogens. What's attached to this carbon?
Hydrogen.
Just 3 hydrogens. So which one takes priority? That one, right? So your groups are going to be 1, 2, 3, and 4 when you number them. Okay? So that's the very first thing that you're going to have to do, is you're going to have to identify the priorities. Okay? So, let me build one of these enantiomers of butanol, and I'm going to use red for the OH, and I'm going to use, there's a methyl. So let's see how we can build these. Butanol, I need 2 other carbons. Right? So I'm going to build enantiomer A as they have it. So here's my chiral center. Okay, so in the plane of the board is going to be my OH and my other carbons. Those are in the plane of the board. This is in the plane of the board. All of this is in the plane of the board, okay? My CH3 is coming out towards me, and my hydrogen is away from me, so I'm going to put it on the back. All right, will everybody agree that I just made molecule A? Methyl group is coming towards me, hydrogen is going away from me, and all of this is in the plane of the board. Okay, so we just built it. The nice thing about building a model, no matter how I rotate things, that center doesn't change unless I break a bond. So it's kind of nice. All right. So now what we're going to have to do is we're going to have to assign priorities, right? So OH is clearly going to be number 1 because oxygen is the highest priority. Hydrogen is going to be number 4. I know that. I know this group here, this ethyl group, if you will, is going to be my second priority, and I know this is going to be my third priority. Okay? So I've got the priorities assigned. How can you do that when you're building a model? Get a little bit of masking tape and just put a little masking tape on it and just write down the numbers. Or on your paper, you can just write down what the different groups are if you want to do that. But for people starting out, a little bit of masking tape works really well. And it comes off, it doesn't make a whole lot of a mess, especially if you use the blue painter's tape. Not too bad, works pretty well. I've seen people also use little sticky notes. Those don't tend to stay on very good though. And I've also seen people throw these to the side and get colored marshmallows. And then they eat them as they go, which is kind of cool. But you can do it any way you want. So we have just built an enantiomer A. But I can't go around and tell people A2-butanol. It doesn't mean anything, right? So we have to name it as either R or S. So we've done the priorities. Now, the rule is, and you have to use this rule, there is no flexibility in this rule. You grab the lowest priority group in your hand and you turn it away from you. You want to make sure that the lowest priority group, whatever it is away from you. So hold it in your hand, just like that. And what I notice when I do that is I have my 3 groups sticking out here. And I notice that it goes priority 1, priority 2, priority 3, and it's going in what direction? Clockwise. Or if you were driving your car, you would be turning to the right. R is right. This is R. This is the R enantiomer. This is R2-butanol. R in italics, -2-butanol. Okay? It is very, very important, and you all will miss this until you practice it. You have to have that lowest priority group away from you. It's important. Think about this. How many people have been to London? Anybody been to London? Okay, we've got 1 or 2 people who have been to London. Did you go see Big Ben? All right, went and saw Big Ben. When you were sitting outside and you were watching the time, which way did it go? It went clockwise, right? Like it should. What if you took the tour up into Big Ben and you're up there in the mechanism and you're looking from the inside out? How does it look like time's going? Counterclockwise. Are you getting younger?
Yeah.
No. You are not. Oh. No, you're not getting younger, right? You're looking at it wrong. It's not how it was intended to be. The lowest priority group has to be away from you. If you turn it the other way, it looks like it's going 1, 2, 3. It looks like it's going counterclockwise. So if the lowest priority group is facing you, it's going to be the opposite of what you think it is, looking at it that way. But always grab that lowest priority group, turn it away, and you'll be good to go. Okay? You all can use your model kits on the exam. You can bring some masking tape, some stickies, or marshmallows. You want to have marshmallows. That's fine too. Okay? Whatever you want to do. Are there any questions about that? Does it make sense? Yeah.
Can you show us what S looks
If I take these two groups,
Uh-huh.
or these two groups, and I swap them, I get the S.
Okay.
So watch what happens if I just do this. Now I turn it away from me. 1, 2, 3, that's the S. Now watch what happens when I leave these two alone and I swap these two. Now I have the R again. Anytime you swap any two groups on a chiral center, you'll get the opposite enantiomer. So if I drew the R for you and I said, give me the S, all you gotta do is swap two groups. You can swap the two groups in the plane, or you can swap two groups otherwise. Any two groups will do it, okay?
So when we're counting, we should be doing up a number to determine clockwise or counterclockwise?
Lowest to highest. Lowest number is highest priority. 1, 2, 3, going in the right. So that would be the R enantiomer. I'm turning my wheel to the right. S, turning my wheel to the left. Doesn't quite roll off the tongue as well as R to the right, but you know, since there's only two possibilities, you only need one. To know one, then you automatically know the other. Okay? You must memorize these rules. Can you write them down and have them in your notes and bring them to class for the exam? Absolutely. It's going to take time. This needs to be committed to memory. Okay? So if I threw a molecule out at you and said, figure it out, you need to figure it out without having to rely on your notes to determine at least the rules. And if, as you all know, I will give you a periodic table, so you'll be able to determine the priorities of any of the elements that are added. Okay? So we just talked about that. So, now, I want you all to get together. I want you to build that model with your model kit, and then tell me whether or not it's R or S. Put your pieces together. We'll make sure you put them together, slot to slot. Makes a difference in your bond making. All right. You should have come up with something that looks like this. All right, so this is the stereogenic carbon, the carbon with the solid dash and the dashed wedge, right? And so the hydrogen is going to be my white sphere, and it's coming towards me. The OH is going away from me. That's my red sphere. And then notice I've got this CH3 and this CH in the line in the plane of the board. So once I'm convinced that I have built that model, now what do? I can assign priorities, right? And I think you all will agree that the OH is going to be number 1, the hydrogen is going to be number 4. Which one of these is going to be number 2? The CH. This one, right? That's going to be number 2, right? Because if I think about it, this is a carbon that's attached to 3 hydrogens. This is a carbon that is attached to 2 carbons and a hydrogen. So this group takes priority. So this is higher priority, this is lower priority. So it's going to be 1, 2, 3. I'm looking at it backwards. So now what do? I heard somebody say grab and turn, right? This is 3. The CH3 is number 3. Yep. This one. This one is number 2. So I'm going to grab my hydrogen, I'm going to turn it away from me. Which way is it going? If I go 1, 2, 3, which way is that? Counterclockwise or to the left, so we're going to call that S. This is the S enantiomer. How can I make the R enantiomer? All I got to do is swap the red and the white, and then I get the R enantiomer. Okay? You all have to practice building models. When you all are doing your homework, and it asks you to assign R and S, always build the model. I've said that several times for a reason. There are a couple of you in here that are probably really good at 3-dimensional, keeping things straight, but it takes practice, okay? And this helps us do that. So make sure you can convert the model from, or make the model from a drawing, I should say. Does that make sense? Okay. There are going to be times when you run into situations where you have like an alkene or a carbonyl, a C double bond O, and you're going to have to decide, is that higher or lower priority? Remember that a carbon doubly bound to an oxygen is just like that carbon being bound to 2 oxygens. A carbon of an alkene, this carbon it's just like it's being bound to 2 other carbons. So you need to keep that in mind as you're assigning priority. I'm going to keep it pretty simple for you on our exams, since this is 251. I'm not going to give you a lot of complicated things that you have to go like 6 atoms out to figure out what the difference is. It's going to be really close to the chiral center. Okay? But you might still have to go out a little bit, just like the ethyl group versus the methyl group. We had to go out at least 1 other carbon atom. Okay? So keep that in mind. And enantiomers have physical properties that are the same as each other and some that are different. And this is going to be important. Okay? When we have an equal amount of 2 enantiomers, we call that a racemic mixture. We learned that last time, right? We, as a class, made a racemic mixture of our model last time, right? I went around and yours and mine matched, and yours and mine didn't match, and we went around and we figured out that it was we all made 50-50 mix. Okay? So a racemic mixture. Some people also call these racemates. This is what happens if you randomly attach the atoms together. You get a racemic mixture. There are some reactions that give racemic mixtures, and we'll talk about those a little bit, not too much. Okay? But if we take 2 enantiomers, we're going to call them A and B, okay? And if I gave one of you A and I gave one of you B and I said, go figure out what the melting point is, you would come back and you would tell me, oh, mine melted at, let's say, 100 degrees, and the other person would come back and say, well, mine also melted at 100 degrees. They have identical melting points. If I gave you 2 chiral liquids, one of them, one enantiomer, the other, I asked you to go figure out the boiling point. A person would come back and say, you know, mine boils at 98 degrees, and the other person, strange, mine does too. Huh. So they got identical melting points, they got identical boiling points. But if I asked you to go take it and put it in this special instrument that we call a polarimeter, one of you would come back and say, wait a second, mine rotated the plane of polarized light clockwise. And the other person would come back and say, wait a second, no, mine went counterclockwise. Optical rotation is the one thing that we can use to distinguish one enantiomer from another. There are a couple other techniques we'll talk a little bit about, but this was the early one. What is plane polarized light? Has anybody ever heard of a polarizer before? Anybody have fancy sunglasses that you like to wear when you're out on the water so it cuts down on the glare? What are those called? Polarizing sunglasses. Okay? Glare comes to you from the water because the light is a wave, and the wave is going in all sorts of directions. You got a wave in this direction, you got a wave in this direction, and it creates glare. That's what glare is. And when you put on your polarizing sunglasses, what does it do? It blocks out most of the wave, directions of wave, and only allows one through. Okay? Polarizing sunglasses, cheap or expensive? They can be expensive, right? Because it takes a special material to do that. But what I can do is I can take a molecule and I can put it in a machine that uses a polarizer, and I can determine how that molecule will rotate the plane of polarized light. And it's kind of cool. And I wish I could explain to you the physics of it, but I don't even know myself the physics of it. Okay? But I know it happens. I know that one enantiomer will rotate plane polarized light in one direction, the other will rotate it in exactly the opposite direction and by the same amount. Okay? So this is something that we can use. I also know that a racemic mixture won't rotate plane polarized light at all. I also know that anything that's not chiral will not rotate plane polarized light. Okay? So I can determine whether or not I have a racemic mixture or one enantiomer or the other by seeing how this molecule rotates plane polarized light. I used to have a little demonstration. I can't use it anymore because we don't really have the old projectors. But I built a little polarimeter to show this to you all at one point. Kind of cool. Got some old material from an old polarizing sunglasses, and that's how I made a polarimeter. Okay. So let's talk about some other chemical properties. Here's something else. Odor is different for enantiomers. The smell. So this is carvone. You can see the chiral center, right? This is S-carvone. This is R-carvone. They're just enantiomers of one another. But if I gave you a bottle of S-carvone and you smelled it, you would say, that smells like caraway seeds. And if I gave you a bottle of R-carvone and you smelled it, you would say, wow, that smells like spearmint. But you know that caraway seeds are very different than spearmint, right? They are different enantiomers. Mother Nature and caraway seeds, for whatever reason, I don't know, makes the S enantiomer of carvone. Spearmint leaves make the R enantiomer of R-carvone. And R-carvone is used as a insecticide. That's why the plants make this. It's very toxic to flies, this type of stuff. Okay, so while it smells good, you all use it in your food, and etc. It's nature's insecticide. It just doesn't hurt humans. Okay, so it's kind of cool. Okay, but it has different odors. Why do you suppose our noses recognize those differently? What do you think our little smell sensors in our nose are made up of? Chiral molecules or non-chiral molecules? Chiral molecules, right? And just like my hand is chiral, I can put my hand in a right-handed glove, but not in a left-handed glove, right? Well, I've only got one type of sensor. The S enantiomer interacts with that differently than the R, and it gives a different signal that goes to my brain and says spearmint or caraway seeds. Okay? That's why you taste things differently sometimes. Okay? Clearly spearmint tastes different than caraway. right? You can tell the difference in taste on some of these things as well, okay? So, I'm gonna show you the cheap and dirty way of building a polarizer. I actually have one of these polarimeters up in my lab, a research grade one. Costs about $20,000. Very expensive sunglasses, okay, if you will. But this is really all it boils down to. You got a light bulb that produces all kinds of light, ordinary light. And you usually, although it's not shown here, you usually have some kind of filter to make sure it's only one wavelength of light. And it's usually, the wavelength that we use is called the sodium D line, which is 589 nanometers. But that's not important right now. And as the light is showing, ordinary light has the waves of light in all directions. That's what those arrows mean. Well, a compound will not rotate ordinary light because the waves are in all sorts of directions. It just won't happen. But I put a polarizer in front of it, and I only allow one of the types of light to come through. The up and down one here, the wave that's going like this. Okay? So now it's plain polarized. I've gotten rid of all the reflection. Only one wave of the wavelength of the light, well, one wavelength and one direction is coming through. If that molecule, or if that light is going through something that is achiral, which means not chiral, that plane of polarized light will not rotate at all. If it's coming into the sample like this, it's leaving the sample like this. Okay? It should have zero rotation. It's optically inactive. However, if the molecule is chiral, the plane of polarization will rotate as it goes through the tube full of the molecule. It will rotate the plane either clockwise or counterclockwise. And I can measure that with another polarizer. All I got to do is take another piece of sunglasses and start to turn it until I can see the light come through again. If it's turned this way, the light won't come through. And I just turn it until the light comes back through again because it's one single plane, right? Do this next time. Take your plain polarized sunglasses, if you've got a friend that's got another pair, and hold them up to one another and rotate them, and it will get dark, and then it will get light, and it will get dark, and it will get light. And the reason is because it will block out the plane if they're not lined up right. And so all we do is we measure this angle called alpha. We know that it's rotated the plane of polarized light by a certain amount of degrees, okay? And we can determine that very easily. You can determine it manually, or you can buy a $20,000 instrument and let it do it for you. So I actually just put my sample in the instrument, and it spits out a number for me. It makes all kinds of noises, does all this kind of stuff, and then it spits out a number for me, okay? And I know whether or not I've got a chiral compound or the right molecule or whatever it is that I'm looking for based on that, okay? This is called the observed rotation. Alpha is called the observed rotation. We call that alpha observed. But alpha observed is not enough. I can give you, and I can give you the same molecule, tell you to go upstairs and get the rotation, and you might come back with different numbers. He might have made a solution that's very dilute. The other person may have made a solution that's very concentrated. Which one do you think would rotate plane polarized light more, the dilute solution or the concentrated solution? The concentrated solution. The more concentrated that solution is, the more it's going to rotate polarized light because there's more molecules in there to rotate it. Right? It also turns out that if I gave you sample tubes that were of different lengths, you would see different rotations. Why would that matter? So if I gave you a tube that was this long and I gave you a tube that was this long, you'd come back and tell me that it rotated the light more, even if they were at the same concentration. Why is that? Why does length matter? There's more opportunity for the molecules to rotate that plane polarized light, right? And my physics friends would yell at me for everything that I'm telling you because I'm not talking about electric vectors and all this nonsense, okay? We're keeping it simple, okay? And so we have to have a way to know how a molecule really rotates plane polarized light, okay? And the way that we do that is through this equation called specific rotation. And it's alpha in a bracket. And it is equal to the alpha observed divided by the path length, the tube length, times the concentration of the sample. Now, when you all were in general chemistry, what did you learn the units of concentration were? Molar. What are the units here for concentration? Is that molar? It is not. Concentration is in grams per milliliter. Why is that the case? Because that's what Emil Fischer did back in the day when he did this in the 1800s and so on. First example. May even been the late 1700s, I can't remember. So, you're going to take the alpha observed, you're going to divide it by the path length. The path length is in decimeters. And most of the time, because chemists like to not do math, we've always used a 1 decimeter cell. So it's about that long. Isn't that convenient? 1 times anything is anything, right? So it makes the math easy, but it doesn't have to be. Okay, so you're going to have to get the alpha observed, the path length, and the concentration. You do the math, and you can calculate the alpha, the specific rotation. But if you know the specific rotation, and you know 2 of these other things, you can calculate the third. Okay? Anybody live in around New Orleans where there's all the sugar cane that they do stuff with? Anybody ever been around that? Okay, so some of you. They have to determine the concentration of sugar in their syrup. And they do it using polarimetry. They know the specific rotation of pure sugar. They can get an observed rotation for their solution, and they know what the path length is. They can easily determine the concentration just by doing some simple algebraic manipulation. This is going to be the most complicated that we get in math this semester. But you need to know this equation, and you need to know how to convert it into anything I ask you to find. I can give you this, this, and this, and ask you to calculate that. I can give you this, this, and this, and ask you to calculate that. I can give you this, this, and this, and ask you to calculate that. Okay? Does that make sense? All right, so let's...
What I'm hearing is we need a calculator.
You need a calculator. You need a little bit of a calculator. That can't be your phone. Do you really need a calculator? Probably not. The math is pretty simple. I'm not going to usually pick anything that's out of 4 decimal places. I might. But here's a sample problem. And I do use a few extra decimal places. I want you all to solve this. A solution of an optically active substance was made by dissolving 10.2 grams of the substance in water to make 1 liter of solution. The solution was then placed into a polarimeter tube that was 1 decimeter in length. The sample was then warmed to 26 degrees, and the polarimeter indicated that the sample rotated the plane of polarized light at 589 nanometers by negative 1362. Yeah.
Do we need to go into Kelvin or don't we keep it at?
Is there temperature anywhere in my equation?
Oh, okay.
It turns out that temperature does matter, but you don't need it to solve the equation. Concentration changes with temperature, right? So it is important to keep the temperatures steady when you're making the measurement. And we usually take room temperature around 26 degrees to do that.
What does the negative indicate?
The negative means that it's going counterclockwise. It's rotating in a negative direction. Remember, it can rotate either positive or negative, clockwise or anti-clockwise. So what do we know? Okay, we know the length of the sample tube. We're asked to calculate this, right?
Yeah.
Right, so what do I know? I know that that's the equation I need. I know that the rotation is negative 13.62 degrees, right? I know that the path length is 1, conveniently. And I know that my concentration is 10.2 grams in 1,000 milliliters. And then, you know, of course, my math friends would cringe at me writing it like that, although your calculator works perfectly fine. Mathematicians just get snooty about that kind of thing. So I know that 13.62 times 1,000 divided by 10.2 should be my answer. But you could just calculate this out if that's what you wanted, your, and then put it in there however you want it. What do we come up with? What number?
1,335.29.
Sounds pretty right to me. That's a lot of rotating. A circle only rotates 360 degrees, right? So it's rotated it several times as it's coming out. That's a very strong optically active substance. In fact, there probably isn't any real substance that's that strong. The most I've ever seen in anything I've ever made was about 400 degrees. Rotated about 400 degrees.
So this is a higher number than we'll probably see on the test.
Yeah, probably. It was just random numbers I made up. You're also going to hear a term called optical purity or enantiomeric excess. So far, we've been talking about pure enantiomer A and pure enantiomer B. But when we do chemistry, sometimes we don't completely make one enantiomer. We may make one enantiomer in excess of the other. And this is why the examples that I gave you last time, right, are very important. What did we learn about naproxen sodium last time? It was chiral. One enantiomer cured your headache. What did the other enantiomer do? It was a liver toxin. You could die. So if I made naproxen sodium where it was only 90% pure, optically pure, would you want to take it? Probably not, right? Optical purity is taking the percent of one enantiomer, so let's say the percent of enantiomer A minus the percent of enantiomer B, where B is the lower number. We call this enantiomeric excess, or EE. In my lab, when we're doing chiral chemistry, and we do it a lot, again, it's one of my favorite topics, we strive to get 95% or better enantiomeric excess. Okay? 90% EE would be 95% of enantiomer A and 5% of B. I subtract those two and I get 90%. That's enough to kill you in some things. This is why some of your drugs are so expensive, because the Federal Drug Administration, or Food and Drug Administration, excuse me, requires chiral compounds that are drugs to be either enantiomerically pure for the active substance, or you have to prove that the other enantiomer causes no harm. How hard is it to prove that something causes no harm? It's almost impossible. So what does a drug company do when they figure out, oh, enantiomer, the R enantiomer is what's doing the chemistry? You know, it's what's curing your headache. They figure out the chemistry to only make that enantiomer. Because they can go to the Food and Drug Administration and say, this is what is active, this is all we're making, this is what we're putting in the pill, we want to sell it. Okay? It's very hard to prove that the other enantiomer causes no harm. Okay? Let's skip that one for today. A lot of things that you'll make will be made in a racemic form. You'll end up with 50-50, just like we put together our models last time, right? And we need a way of separating one of the enantiomers from the other so that we get the pure enantiomer that we want. But I just told you, right, that enantiomer, the R enantiomer and the S enantiomer of a molecule have exactly the same melting point, they have exactly the same boiling point, right? So what are we going to do to get just the pure enantiomer out of the mixture? We're going to do what's called resolution. And here's an example. We're going to take a carboxylic acid that happens to be chiral. So here's 2-phenylpropanoic acid. Notice they write plus minus. What do you think that means? In parentheses, plus, comma, minus. It can rotate both ways, and it means that it rotates in both ways equally, which means it's racemic. Okay? Plus minus means racemic. It's another thing you'll find in biochem. Okay? So this is racemic 2-phenylpropanoic acid. Don't worry about the name yet. Okay? But what you see is we've got a carboxylic acid, we've got a methyl group, we've got this C6H5 thing, which is a benzene ring, and we got a hydrogen. We can clearly see where the chiral center is. And this means that I've got equal amounts of the right-handed version and the left-handed version. The right-handed version and my left-handed version, right? Okay. And I know that the right-handed version and the left-handed version have the same physical properties. So what am I going to do? Well, I'm going to play a little trick. And I'm going to react it with something called an alkaloid. Don't worry what the structure of the alkaloid is. Alkaloids occur in nature, and they're amines, they're bases. Bases react with acids to make salts. Remember that in Gen Chem? Right, an acid plus a base gives salt. All right, so I'm going to take this chiral racemic acid and I'm going to react it with this alkaloid that Mother Nature has made as only one enantiomer. So think of the alkaloid as my right hand. And think of the phenyl 2-propanoic acid as a assembly line of gloves that are 50-50 right and left-handed. So if I've got a bunch of baseball gloves coming down the assembly line and I want to separate them into the right-handed box and the left-handed box, what can I do? I can take my right hand and I can stick in each one of them. That one fits, so it goes in the right-handed. This one doesn't fit, so it goes in the left-handed. And that's how I can separate them. I can use my one hand and I can separate it because my right hand in the right glove fits differently than my right hand in the left glove. They are different. They have different physical properties. And so what happens is I end up with this salt, right, where I end up with a plus-minus salt, and I end up with a minus-minus salt. They are diastereomers of one another. They are not mirror images. Therefore, they don't have to have the same physical properties. They can boil at different temperatures. They can melt at different temperatures. One might crystallize and the other won't. And that's what we're going to use. We're going to use crystallization here. So what happens is I take that mixture and I put it in my refrigerator for about a week, and I come back and there's these beautiful crystals that are grown. And I filter those crystals off and I wash them and I take good care of them. And it might be the plus-minus salt that crystallized, let's just say that. And so now, when I look at this, right, I've only got the positive enantiomer from my phenyl 2-propanoic acid. I just have to figure out how to get it away from the salt. You all are going to learn about this when you do extraction in lab. I think you got an extraction lab. Have you all done that yet? You'll do an extraction lab where you'll learn about how you can separate things like this. Okay? So we're not going to worry too much about it. But the take home here is that we can resolve it using what Mother Nature has given us. And alkaloids are typically cheap, readily available, and they're enantiomerically pure because Mother Nature made them.
So you still result in the same amount of each?
You will have 50-50. You'll have 50% of it over here. The other 50% will be over here. This, however, you end up throwing away because it's not what you want if you wanted the positive one. So it's kind of wasteful, but it is one of the ways to get what you need out. The pharmaceutical companies still use this method for things that they can't make in one enantiomer. They'll make it racemic. They'll throw in some kind of what we call a resolving agent, in this case an alkaloid. They'll try to recrystallize it. And as you can imagine, that adds to the cost because they're throwing away half their molecule as the enantiomer that they don't want. So they try not to do it, but sometimes they have to. Okay. There's another way in which we can separate enantiomers called chiral chromatography. This is my favorite way of resolving enantiomers. This is actually an experiment that we did up in my laboratory. Okay. This is called a chromatogram, by the way. And what do we see here? We see a peak, and we see another peak. 2 peaks. Why do I have 2 peaks?
So you have two things.
Because I have 2 enantiomers. Exactly right. So in my lab, what we do is we take these molecules, okay, and we convert them into these carboxylic acid. So it's a carboxylic acid here. This functional group is called an ester. I've got a methyl group here, and then I've got this other group that we don't have to worry about naming. And this is the R configuration, if you look at this, okay? So it is actually 1, 2, 3. It's in the R direction, okay? That is not a hydrogen, that's a methyl group. But in this case, the methyl group is the lowest priority group. All right? When I make the racemic version of this, I get a chromatogram that looks like this. The material that I pass this through is chiral. And so one enantiomer will interact with the column differently, and it will elute at a different time. Okay? And so I can actually just, as these are coming off the chromatography column, I can just collect this peak, and I can collect that peak, and have my enantiomers separated. Okay? But this is racemic. I can also take this molecule and I can feed it to pig liver esterase. It's the enzyme that we're famous for in my lab. So we actually take, well, we don't, we buy it now, but you can actually take a pig liver, grind it up, and there's an enzyme that will convert one of these esters into a carboxylic acid. And it's an enzyme, so it's made of amino acids, so it's chiral. And what it will do is it will preferentially hydrolyze it to the R enantiomer. And you can tell that by looking at this. Notice the peaks are no longer the same size. This one is quite a bit smaller than this one. I'm making this in 63% enantiomeric excess. Okay? We try to get to 95%. So we played around with the chemistry and tried to figure out how to make the chemistry better. And we finally figured it out. Okay? But I wanted to show you that even things in nature sometimes give mixtures, although it prefers one over the other. So in my lab, we're kind of famous for working with pig liver esterase. It's cheap. It does its job really well. A lot of people kind of get grossed out about working with pig liver, but it works really well for us, and we can make these types of molecules that we go on and do other things with. Okay? And so here's how chromatography works. So you have a column. This is just an example. This is not the real column that we use, but it's just, it's made, this one's made of glass, so you can see on the inside. There's a solid material on the inside that is made of basically of fine ground sand, and it's got a chiral molecule that's attached to it. And as you put your molecule on and you flow solvent through it, one of the enantiomers will stick to the column more, because it's like a right hand and a right glove, and the other one will not interact with the column as well. It's like the right hand and the left glove. And so they will start to separate out on the column, and one will come out first, and then the other one will eventually come out, just like we saw on the chromatogram. Okay? And so this is how we can purify. Have you all done any chromatography yet in the lab? No? Well, when you get to that point, you're going to learn how you can actually use chromatography to separate things, which is kind of cool. Okay, so, but you can learn more about it easy on Wikipedia. I stole these pictures from Wikipedia. All right, so let's wrap this up by talking about some things in our everyday life. A hammer. Is it chiral or achiral? How many people think it's achiral? How many people think it's chiral? It is actually achiral. Why is it achiral? Have any of you ever been to Lowe's to buy tools? Have you ever asked a person for a left-handed hammer? A right-handed hammer? Nope. You just go buy a hammer. It's achiral. If you take the hammer and you turn it on its end where the claw is, you'll see that there's a mirror plane that runs right down the middle of it. So a hammer works just as well in your right hand as it does in your left, if you're left-handed. Right? For me, it would be my hand. I'm right-handed. Okay? But a hammer is achiral. How about my favorite brandy snifter? Is that chiral or achiral? It is achiral. There's a mirror plane that runs right down through the middle of it. I can take my brandy snifter and its mirror image and they will superimpose on one another. Okay? How about a pair of shears or scissors? Why are they chiral? You're right, they are. You can, can't you? Yeah, now you can go to Lowe's and say, I need a pair of, or Walmart, I need a pair of left-handed scissors. Because your right-handed scissors will not fit in your left hand without it hurting and feeling weird, right? They are chiral, okay? Now you can buy the cheap little paper-safe ones that the kindergartners use that are ambidextrous, yeah. But a good pair of scissors are going to be chiral. What's going on here? How about a boat propeller? It is chiral. It is chiral. There is a twist to a boat propeller along its axis. And if you take that and its mirror image, they are not the same. They're not superimposable. And it turns out when you go buy a boat propeller, you have to know how the twist is on your boat propeller. Because if you get the wrong one and you put it in drive, it goes backwards. You put it in reverse, it goes forwards. Right? It'll go the opposite way. Right? So it's important that you have a boat propeller with the right twist in the molecule or in the material. All right, that finishes us up for today. We have a quiz for chapter 5. I need you to take 5.46, put it on the table on your way out. Please make sure you put your name on it and your ID number. And I will see you all on Tuesday. Have a great weekend.